Video. Okay, so the two things I really want to do today are, well, I want to do three things. I want to do this line. I want to do Cook's theorem, and I want to cover Turing machines. Okay, so we have like 50 minutes left, so hang in there. Okay, so this is something called the Satan transform. So basically the Satan transform, it says that if you're given a formula, you can produce another formula which is in conjunctive normal form, so CNF, which is satisfiable if and only if the original formula was satisfiable. And basically what you're going to do, I forget exactly how to spell Satan. I need a formula. Somebody quickly type a formula into the chat box. This is probably the old marker. So if you had like, yeah, this is the old marker. If you had X and Y or not Y and Z. Something, okay, I'm just going to do something really small, okay? So this is not in conjunctive normal form, okay? And, yeah, okay. So this is not in conjunctive normal form. Conjunctive normal form is a bunch of disjunctions, so ors, and then it's all anded together. So it's only sort of got, it's just a bunch of clauses called ors and just anded together. So what you're going to do is you're going to view this as sort of a binary tree. So the first sort of thing, you have an and of y and z. And then, you have an and y and z, and then you have a not, and then you have an or of this and y, and then you have an and. So let's say the order. I mean, these things. I forget which way these associate. Do logical operations associate? Do you do this way, or do you do it this way? Okay. Well, this definitely happens first. Okay. So we're going to say that, okay, we're going to do this and first, and, okay, I'm going to put the brackets in to make everything clear. And of x and y, and then this is an or. Okay? So, how are you going to do this? Well, for each of these things, you're going to you're going to have a W1, you're going to have a W2, you're going to have a W3, and you're going to have a W4. Okay? And then what you do is you write W1 is true if and only if Y and Z. Okay? W2 is not W1. W3 if and only if X and Y. W4 if and only if W2 or W3. And so these things are all binary. And what you do if you, let's just do this one. So it's W1 is true if and only if, so you can go through and see that you can for any statement where it's like some variable, if and only if, some binary operation on two variables, then you can write that as in conjunctive normal form. Right? So this is going to be either, so, well, okay, it's not, let's, W1, in this case it's an and Y and Z, wait, I have to remember how you do that. You could do that, or, yeah, I'm gonna get an or. So I want to get, so it's either not W1 or not Y or not Z, and W1 or what? Okay. My internet has died. An unknown error occurred. Okay. Zoom. This meeting is yes, okay.
Recording in progress.
Hi, sorry about that. My internet is a bit flaky. Okay, you will believe me. This is, you can take these and just turn them into conjunctive normal forms. So I think it's either this is true or one of these is false. So it's either, if this is false, so it's either this is false or one of these is false, and either this is true or one of these is true. Wait, or something like that. Okay. It will be in the lecture notes. Okay, so this is it. So given a general, any forms, any Boolean, propositional Boolean formula, yeah, I'm sorry it disappeared. Hi. Given any Boolean formula, you can sort of turn it into a CNF formula. Now it doesn't have to be 3 CNF, but if you go through the state and transform, then it turns out that the clauses are always at most 3 literals, and then if they're less than 3, you can always just sort of pad them by repeating one of the literals. It doesn't change anything. So you can actually go from sat to 3 sat. So that means that from any of these, you can turn it into an instance of 3 sat. Yeah, okay, not that. I think it's Russian, so it's a different alphabet, but I think there, or maybe this is with a Y. So, yeah, it's not hard, but the idea is sort of to break this into, to turn this into the tree, and then realize that for each of these, to view it as like a binary, to view it with a circuit with fan in 2, and then realize that for each gate, you can write that gate as CNF. Okay. And then at the end, what you do is you say, okay, W4 has to be true for this to be true, so you have a W4 and and then you have all these statements saying this is equal to these are equal to these are equal to these, but you have these expressed in CNF. Okay. So, now, this Cook's theorem. So are you starting to get a feeling that SAT is powerful? See, you start to, I was doing this because I wanted you to feel like, yeah, if I give you a problem, you can sort of, and it's easy to check a solution. What you can do is sort of write a formula, a polynomial size formula that says, that can sort of express that there is a solution, right? If the solution can be checked in polynomial time, then you can sort of write a poly-size formula. That's a bit hard to see. Now there are other problems which are in here, which are actually more powerful, okay? Well, they seem more powerful at first. For example, there's something called integer linear programming, where you are actually allowed to count. You're actually allowed to say, okay, you can have, you can say, okay, x1 is 1 or 0, x2 is 1 or 0, and then you can say x1 plus x2 plus x3 plus x4 plus all of these is at least k. So it seems easier to constructivist school, possibly a relative. He was, I believe, Russian. I will check. I'm not actually, I know nothing about Satan, the person. Okay, so you think, okay, SAT seems powerful. Now, integer linear programming seems more powerful because it's easier to express, like the clique is of size k. You just say, okay, this variable is 1 if it's in the clique, it's 0 if it's not. You express these inequalities that say you can't have two things which don't have an edge between them. They can't both be 1. And then you say, okay, and then if you sum up all the variables, it's at least k. That's easier. So you want to think about what would be like a really powerful sounding problem. Like this, the class of stuff that can be added to this graph and reduced such that SAT can be turned into the stuff, and the stuff can be turned into SAT, is sort of equivalent to SAT. So this is sort of like the class of stuff equivalent to SAT. If you can solve one of them, you can solve SAT. If you can solve SAT, you can solve one of them. You can solve the rest of them. But that's like, we want something meaty, right? So suppose that now this is going to sound like a really, really powerful problem, okay? I'm going to give you a program. So I don't know, what are we going to call it? We're going to call this input, I don't know, input checker. Is this, oh, is this timer running? Yes. Okay. Input checker. Now this is going to sound like a really, really powerful problem. Input checker is given a program, let's say it's a C program, because C is awesome. Of n characters. And a time bound let's say is polynomial in n. I'm not sure if it makes sense to say that, but okay, let's say, and you're given a program and a time bound t. Okay, so this is an instance. You're given a C program. You're given a time bound t. Let's say the C program is called P. Does P stop and say yes in time t? Now maybe I'm going to edit this a little bit for the course notes. Does this sound like a really powerful problem? Right? If you could solve this if you could solve this in time polynomial in n, yeah, it is, but it has a bound. It has a time bound. So this is actually, Cook likes to say that there is sort of a relationship between P and NP and RE and so recursive and recursively enumerable. So this problem is hard. It's hard, but it's possible, right? Like you could do it but maybe not in polynomial time, right? But you can see that if you could do this, it would be really cool. So in fact, for any problem where you can sit down and you can think, okay, well, if you're given an instance of the problem and somebody gave you a solution and said just check it, and you could write a little algorithm to check it, then if you could solve, suppose that for problem A, you can check a solution in polytype. Right? Then what does it mean, like you could check it? Well, we're computer scientists. To us, that means you could write a program to check it. Right? And since we believe that C is amazing, you could write a C program to check it. So if somebody gives you an instance, you can write, if somebody gives you the solution for A, you can write a C program. But that means to check it. And that means if you take your C program that checks solutions for A, right, you can work out how long it's going to take for instance A to check a solution. You can, if it's polynomial time, T is going to be polynomial. So you're going to say, okay, if you could do this problem, if you could solve this in polynomial time, then you could solve A, right? Because you would just you can check a solution. We're going to replace that by, you can write a program, a C program, that checks solutions in polytime. So suppose you can write a C program that checks solutions in polytime. Okay, so what you're going to do, given an instance of A, you turn it into a program. That's going to take polynomial time, right? And we hope that the program to check, if you can check it in polynomial time, that means you can write the program in polynomial time. The program is polynomial size. And then the program, you can work out the time bound that the program is going to need. Yeah, it's not as hard as the halting problem. Like the halting problem, you could, this is the important thing, an important thing. If you had the halting problem, you could reduce SAT, you could reduce clique to the halting problem. But not the other way around. Right? So the halting problem is not in NP because it's too hard. So this is so people like to say, okay, how do you show that a problem is NP complete? You show that it's in NP. That means it reduces to SAT. This is usually the easy step. And you show that you can reduce some other polynomial NP-complete problem to it. So halting, you can reduce any of these problems to halting, but you can't reduce halting the other way. So it's not in this sort of equivalence class. Okay. So, but we're doing Cook's theorem right now. Okay. So Cook's theorem, if I told you, believe me that input checker is a powerful problem. Okay. If we could solve input checker in polynomial time, so you give me a program, you give me a time bound, and you say, okay, does this program, the size of this program, if I can tell whether it stops in a given amount of time, in time polynomial and the size of the instance, then I can solve a lot of problems. Maybe t has to be polynomial. Okay, I'll think about this for the lecture notes. Okay, you believe me that if I could solve input checker, if I could solve input checker in polynomial time, I could solve in polynomial time all of the problems for which we can check a solution in polytime. It would mean that you can then find a solution in polytime. Okay. So if there exists a polynomial time algorithm for input checker, given the program, tell if there is an input that makes it say yes, then any problem, and if we can solve that in polytime, for any problem where you can write it, you can check it, then you can solve it. Okay? Do you believe it? Do you see that this is like, it's not that surprising. I mean, look, it's super powerful. Okay, I'm just going to have to trust that people are listening and believe me. I'm down to 15 people. Okay. So, somewhere, I'm going to draw this here. I'm going to draw input checker here. Does p stop? Let's say program. Oh, sorry. This is, I made it sound too much like the halting problem. I need more sleep. Is there an input to P such that it stops? And says yes in time t. Okay? Now this is, okay, right, yeah, otherwise you would just run the program. Sorry, this is, I shouldn't have stayed up working on that problem. Okay, this, so yeah, that's why it's called input checker. Sorry. So you can look at it and say, is there some input that makes it say yes? Well, okay, if you have for colorability, you write a little program that, given a graph, you write a little program that checks whether a coloring assignment, a color assignment to the vertices of that graph, it just checks, is that a for coloring? So for that graph, you have a little program, and you just say, okay, is there an input? And it checks an input. And you say, is there an input that makes it say yes? There is an input that makes it say yes if and only if there is a for coloring. Okay? Sorry. So, you believe that this is a hard problem. If we could solve this, we could solve all of these. So I'm going to say input checker, obviously sat reduces to this, clique reduces to this, other stuff reduces, the hand path reduces, all of these things